Hey guys, how you doing? Hope you're doing well. Just giving the others a few minutes to join us, and while I just mop up some administrative duties here, need to send something to the principal. So in the meantime, I'm going to ask that you just go on to some reading. I will come to you in just a few minutes. Just need to send my principal an email. All right? That's okay?
Okay, sir.
Nice. Thank you.
Okay, sir.
Come on.
Good evening, sir.
All right. This is now 20 past. I am not waiting any longer. Um, we need to begin. So let me again officially, for those who just joined, let me just officially say good afternoon to you all. Trust that you are Ankidori. You're all well and ready to go. Any comments, any concerns, any commendations? Anybody want to share anything? Anything exciting happened to you at school today? I mean, at work today?
Oh, sir, good evening. I sent you a message in Zoom chat.
Okay, all right. So I'm on two devices. So let me just check to see which is which. All right, I think this is the one you sent it on. That happened to me on Monday when I was trying to do something too. Understood. Understood. All right. I have this thing. I don't know what to do. Let me just switch. All right. All right. So it was asking me to switch devices. So so as not to have any difficulties. I complied. All right. So, all right. So I see the ones that are here. Where's Kylo? Kylo has not been coming to class. I don't see Kylo. I never saw Kylo on Monday, and he's not here tonight. We need to give the boy a call. All right. So we have in our possession. Two videos. That's all right. Just see if we can use one ear to listen and the other ear to listen for the card in here. But I might not make it up too. And then you go blame me, say media card upon you. Just be safe, please. And conceal your phones. If you're, for those of you who are in transit, please, we don't want nobody come holding up. All right, no problem. All right, so in our position, we have two videos, and I'm hearing comments like, oh, yes, sir, we like one over the other. That's fine. Don't have a problem with that either. So what you want us to do, you want us to talk about the creationist view first, or you want us to go with the inflation? Which one? You choose which one you want us to start with first.
Can do the inflation first.
Inflation.
Then I the inflation. So you're going to talk about inflation. All right. Let us spend some time on it.
Sir.
Yes, dearest.
Before you go to the inflation, the inflationary, we call it epi. Is it different from the inflation theory? Because I'm kind of confused.
All right, no problem. We're going to have the clarification.
Okay.
We're going to have the clarification. Who I can find. Let me see if I can. Share them both. Data or Wi-Fi. Come on. Are you seeing the screen?
Sorry, it's loading.
Just saying that you start sharing screen.
All right, never mind. I'll stop it. I see my screen now?
Yes, sir.
All right, let me know if you hear the audio. Are you?
No, sir.
Nope.
Not hearing the audio. Okay, hold on. Audio settings. I need to share audio. Let me know if you're hearing it now. Hearing it?
No, sir, we're not hearing it.
Oh, hold on again, please. Are you hearing it now? Are you hearing it?
No, sir.
All right, guess what? Clearly my old system now works. All right, is there anyone in the class that is available to share the document for me? Please.
Sir, I can share.
I'll go ahead and let me just stop share. Thank you very much for bailing me out right here. Oh man, system failed me. How dare you?
One second, sir.
Cosmic inflation describes a period of insane exponential expansion right after the instant of the Big Bang. It calls into question our very understanding of what the beginning of the universe even means. The Big Bang theory describes the earliest epochs of our universe amazingly well, and has made predictions that have been verified beyond reasonable doubt. But two significant problems with the simple model tell us that something strange must have happened in early times, an insane growth spurt that we call inflation. Today, I want to explain what inflation is, why we need it, and why essentially all cosmologists believe that it really happened. The observable universe is impossibly huge, and I'm not exaggerating the situation here. It's so huge, 93 billion light years from one edge to the other, that those most distant points should never have had time to communicate with each other. And yet, at some point in the distant past, they must have been in contact. The cosmic microwave background tells us that they were once close enough together to become perfectly smoothly mixed. This smoothness of the CMB is called the horizon problem, and we talk about it in the last video. The horizon problem isn't the only troubling feature of the CMB. We can use the apparent size of the very subtle fluctuations in the CMB to measure the flatness of the fabric of the universe, of space-time? And the answer we get is very strange. Let me explain. A flat sheet of paper is flat, duh. Draw any triangle on one and add up the angles. It's always 180 degrees. Draw the same triangle on the surface of a sphere, which has what we call positive curvature, and the angles add up to more than 180. On a negative curvature, hyperbolic plane, a saddle-like structure, they add up to less. Triangles in 3D space obey exactly the same rules as on 2D surfaces, and their geometry measures the curvature of space. So now, think of those blobs in the CMB as the ends of very, very long triangles. We know the size of the brightest of those blobs. They're defined by how far sound waves could have travelled by the time the CMB was created. And we know how far away they are. They're really, really far. Using basic trigonometry, those distances tell us what the little angle at this end should be. It should be 1 degree, assuming the universe is flat. It should be larger if the universe is positively curved, smaller if negatively curved. And yes, it's pretty much exactly 1 degree. Based on the precision of our measurements so far, we know that the curvature is within 0.4 of 1% of perfect flatness. Okay, so what? The universe is flat. No, actually it's extremely weird. An expanding universe doesn't tend to stay flat, even if it starts that way. Analogy. One way to bowl a strike is to keep the ball near the centre of the alley all the way to the pins. If the ball isn't moving fast enough, then any initial deviation from dead centre will send it towards the gutter. Same with the universe. If the centre of the alley represents a flat universe, then the gutters represent extreme curvature in the positive or negative directions. If the universe starts out even a little bit not flat, then that not flatness will amplify quickly. So, if our universe is flat to within 0.4% now, then in the first instant, the universe had to be flat to 1 part in 10 to the power of 62. That's like rolling your ball really, really slowly and having it stay within 0.4% of the center of the alley. And the alley is a light year long. Nice bowling, universe. This flatness problem is just as much of an issue as the horizon problem. Both seem strange if we assume that regular gravity was always the only force affecting the rate of expansion after the initial kick of the Big Bang. We need to throw out that assumption because it's giving us the wrong answer. That's a science thing, questioning your assumptions. Try it, it's fun. So it turns out that we can fix both of these problems with a single elegant idea called inflation. It goes like this. Start with a universe so crunched down that the entire currently observable part of it was all causally connected. Then, for a very short period of time, blow it up much faster than the speed of light so that most of it appears causally disconnected, at which point inflation stops and regular expansion takes over. This works because even a very blotchy, curvy universe is going to be much smoother and flatter on its smaller scales. Inflation takes a very tiny, smooth, flat speck of that blotchy, curvy, greater universe and blows it up to a macroscopic volume really, really fast. That inflated speck subsequently grows into the universe that we know, but retains its once subatomic smoothness and flatness. That's right, according to inflation, the universe that we see is a tiny part of a vastly larger universe that itself may well be curved. The neatness with which this inflation solves both the horizon and flatness problems really has most cosmologists thinking that something like this must have happened. For this to work, that inflationary expansion had to throw neighbouring regions of space apart at many times faster than the speed of light. It needed to increase the size of the universe by a factor of at least 10 to the power of 26 in less than 10 to the minus 32 seconds, ending when the universe was just macroscopic, something you could hold in your hand. In the subsequent 13.7 billion years since, the universe has expanded by about the same amount that it did during inflation. So what sort of mad physics could do something like that? Actually, Einstein came up with the exact mathematical description that we need. An anti-gravity term called the cosmological constant in the field equations of his general theory of relativity. He added this as a way to allow his theory to describe a static space-time, a universe that's neither expanding nor contracting. When it was later discovered that the universe is indeed expanding, Einstein retracted his constant. But this bit of math gives us exactly the type of expansion that we need for inflation. Incidentally, it also describes the effect of dark energy, and that may not be a coincidence. The cosmological constant represents something that can happen to our space-time. Einstein is right, even when he's wrong. The cosmological constant adds some energetic stuff to empty space. It doesn't tell us what this stuff is, just that it's a property of space itself, and that it acts to drive expansion. The more space, the more of this stuff, and so the more space, the more expansion. We'll delve pretty deep into how this works in terms of general relativity on a future episode on dark energy. And we'll explore exactly what could cause such a weird sort of energetic vacuum real soon. Inflatons, scalar fields, false vacuums, all of that. For now, let's just go with the fact that empty space can propel its own expansion, and will do so if the vacuum contains a ubiquitous constant energy density. Another really important thing about the driving mechanism of inflation is that it stopped. The universe slowed down from exponential to the regular old expansion that we see today, what we call Hubble Expansion. And while we know the minimum amount of inflation needed before that stopping point, we don't really know when it began, or even if it had a beginning. It may have, and there are some ideas about what got it started, but it's also possible that inflationary expansion is the default state of the greater universe. I should say multiverse at this point. This is the idea of eternal inflation. I'll get to all of these wild ideas very soon. With inflation, the Big Bang Theory takes on new meaning. When first conceived, the inflationary period was thought to have started at a particular point after the instant of the Big Bang. But once you accept inflation, there isn't necessarily a good reason to think that there was a normal expansion period before, if there even was a before inflation. In fact, the instant that inflation ended can perhaps be thought of as the moment that our universe, as we know it, came into being. In that sense, inflation is the initial kick of the Big Bang. We don't need to talk about an exploding singularity at all. Time may not have begun with the Big Bang, and so we'll rewind to before the beginning of the universe, very soon on Spacetime. In a recent episode, we told you why space things are the shape they are, and you guys brought it with the big questions. Frank Schneider asks, why does dark matter in a galaxy seem to form a sphere? Well, this is because dark matter doesn't really interact with itself, except gravitationally. The Milky Way and our solar system were originally made of gas, giant clouds of the stuff. And gas does interact with itself. It drags on itself. So even though the gas originally had motion in many directions, over time it sweeps into a single bulk flow. Dark matter doesn't sweep itself. It just passes by with a tiny gravitational tug. So the orbits of any bit of dark matter can be in any orientation or direction, and random orientation orbits give you a spheroid. This is also true of the stars in elliptical galaxies. Stars are small enough compared to the distances between them that they can be in these random orbits. The reason spiral galaxies are disky is that those disks formed before the stars actually formed, back when the material was mostly gas. D. Blanding and a few others questioned my use of the concept of a centrifugal force. And deblanding, I definitely chose yours because of your particular phrasing. It's true that this force is in a sense fictitious. It emerges in a rotating reference frame as a force-like term that resists inward motion. It doesn't exist in the inertial reference frames for which Newton's laws are valid. For example, in a reference frame of an unmoving centre of mass, you have a centre-pointing or centripetal force, in this case that's gravity, acting on the orbiting object, and the force is resisted by nothing. The orbiting object is subject to the full acceleration caused by gravity, which is what causes it to move in an orbit. In that reference frame, it's the velocity perpendicular to the centripetal acceleration that resists radial infall. But centrifugal force is easier to say, and it's still accurate. A couple of you asked about the shape of a black hole and its accretion disk, based on the spin of the black hole. Okay, so first, the accretion disk that forms around a black hole can either be very flat or fatter, but probably more toroidal than spherical. Yet that doesn't have much to do with the spin of the black hole itself. It depends more on things like the rate of accretion, the viscosity of the material, the way angular momentum is lost by that material, stuff like that. Although the magnetic field of a spinning black hole can also play a part here. However, the shape of the event horizon of the black hole itself does depend on spin. And indeed, a rapidly rotating Kerr black hole is flattened, it's an oblate spheroid, while a non-rotating Schwarzschild black hole is a perfect sphere. Omicron Vega asks if I can please do the blue steel face from Zoolander. I'm sorry, I only do Magnum.
So should I play the other one now?
Yes, that's one.
Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies, et cetera, et cetera. So the way in which inflation explains the bang is in terms of a very surprising feature of physics, I think very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity. But that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. And furthermore, modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsive form of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity. Once you decide that this mechanism of propulsion is very likely the way our universe was born, you can ask what kind of universe does it predict and does it agree with what we see. And in fact, it allows us to understand three very important properties of our universe. One is it allows us to understand the uniformity of our universe. As I think was already mentioned, this cosmic background radiation that has been now measured with incredible precision has fluctuations which are incredibly interesting, and we'll be talking about them tonight. But these fluctuations are incredibly tiny. They're only at the level of 1 part in 100,000. To an accuracy of 1 part in 100,000, the cosmic background radiation that we see is the same intensity in every direction that we look. The universe is just unbelievably uniform on large scales. And that cannot be understood in the conventional Big Bang picture. But inflation explains it very naturally. You start with a very small universe, which becomes uniform before inflation, And then inflation just takes over and magnifies this tiny uniform speck to become large enough to include everything that we observe.
So the moment the inflationary period ended, we were together enough to have produced the uniformity that we see today, and that post-inflation period, everything kind of got disconnected and clumpy and all of that, but the conditions for uniformity were already set in the inflation period.
Absolutely, right. That's the picture.
Doing all right, doing all right.
Mad science. Whew. Thanks, Joe. Questions, comments? What say you? Talk to me. What have you seen? What comments do you have? What is it that you see? What is it that you don't see?
For me personally, I think the second video was a bit more simple than the first one to understand.
All right, so the first one, and I'm coming back to you guys. The first one is deep. It's very deep. Lots of their explanation was mathematically derived. Say something, Benika?
Oh yes, I was just agreeing that it was more complex.
Yeah, right. So it was more mathematically derived in its explanation. But technically, they both are saying the same thing. It's just that this guy, Alan, would have simplified matter in a lot of sense. But if you look back at it, I mean, yes, this is a simplified version, but both are saying the same thing. So this is what it is that I'm saying to you. This is not the end all for what it is that we would read to understand the whole business of the inflationary theory. We will have to read more in order to get what it is that it is saying, because in essence, let me not even tell you my viewpoint. I need to know how many of you are understanding, even out of the 2 seconds, the 2.5 minutes video. So yes, I agree. The second of the two was more simplified, and I agree. I won't even debate that. But the first is also giving a lot of information, but it is a lot of mathematics inside of it, and I will try and simplify what is happening, because there's a myth in all of this, and I just want to help you to simplify. But let me hear from the others though. What say you? What did you take away from the videos?
Sir, to be honest,
some
of it, it's still kind of little unclear for me.
Okay, all right, no problem.
Yes, sir. I don't really understand it clearly, but is it that the Big Bang theory was first, but after the theory of the inflation, they believe that inflation was there before the Big Bang theory?
Okay, let me ask a question. Which occurrences took place first? Was it the Big Bang or the inflation?
Mr. The Big Bang.
Yeah. I don't hear you.
The Big Bang?
So it is after the Big Bang that we have the inflationary stuff taking place. So the Big Bang came. Say it again. Paz, you were coming in. So what it is that you need to say?
Oh, sir. That's the point I was actually going to make. From what I understood from the video, that the inflation theory basically came after the Big Bang.
Come on. And that's why I did the Big Bang first, because there are several things. Remember, you remember they talk about the CMB? The CMB is a cosmic microwave background, right? And that was developed as a result of what? The Big Bang. So it's after the Big Bang that we have this sort of cosmic, the CB, the cosmic, or the CMB, the cosmic microwave background, because it's like a frying of something, So I don't want to get you yet. I want to ask. I'm coming back to you with that point. I'm coming back to you with that point. I just need to hear from somebody. So I just want to see how many of you are. And I have no problem in it, that you read it or you watch it and don't get it. It's not a problem. But at least you're actively doing something. What else? Somebody else before I move in.
Oh, sir, remember the question I was asking about the inflammatory epi versus the inflation theory. So I was just looking at it because it's still confusing me. I realized the same inflationary epic was in the Big Bang theory, and it spoke about the expansion, and it also spoke about the different forces that disappeared. When I was going through the Big Bang theory, I also saw that the first step was where gravity disappeared. I was thinking about the inflation theory when he spoke about instead of gravity attracting, it was we call it repulsing. So it was pushing back, right? So I was thinking that gravity in the Big Bang theory it never really disappeared. It did that action where it pushed instead of pull. So I don't know if I'm thinking too much.
No. And that's where we want to go. That's where we want to go. Could we have inflation if there was no stretching?
No. I don't think so, sir.
No, it couldn't. Because remember, it is as a result of the stretching and the space that is there, that is creating the inflation, the inflation in the universe. Question now. I did say to you that the first video is highly mathematical. No, when you're using trigonometry on a flat surface, a two-dimensional surface as opposed to a three-dimensional surface. The three-dimensional surface is a sphere, the globe, that we commonly know it as. Yes, you can have a triangle on a globe, but the angles in that globe will not measure 360 as for the 2D. The 2D will measure, not 360, 180. The 2D will measure 180. So irrespective of which triangle you draw, scaling, obtuse, equilateral, right angle, it no matter. The sum of angles in a triangle, a two-dimensional triangle, is going to add up to 180 degrees. But for the sphere, it's not going to happen. And I might tell you that the sphere has 3 right angle triangles. So it's going to add up to 270. All right? Now, what I understand from it is that this inflation causes the universe to be more flattened. Anybody got that from it?
Yes, sir.
Yeah, man. It has caused the flattening of the universe. So, which it now moves from 270 degrees per triangle to now 180. So it is actually reducing it. And then it speaks about the negative rotation versus positive rotation. If there's negative rotation, it's going to be less, positive rotation is going to be more. All right? So this inflation has caused, because of the stretching, and now you're talking about the distance between different spots, hot spots on it. When you connect those hot spots, you are getting a more flattened universe. How do we know that? And that's what I'm saying to you. Both videos are saying the same thing, just that one of the videos is actually more simplified than the other. How do they know that it is causing the flattening of the universe? Because remember, I said to you, in a two-dimensional figure, the sum of angles in a triangle is going to give you 180 degrees. The sum of angles in a triangle is going to give you 180 degrees. However, when you plot the angle in a triangle on a sphere, they don't add up to 180 degrees. They add up to more than 180 degrees, right? But when the cosmologists now are doing their calculations, they are recognizing that it is tending to how much? Let me see if you follow my argument now. What number of degree is it tending to when you look at that triangle? Oh, I think I'm muted. We're not here.
What number, sir?
Yeah. What degree? What total degree is it? Is the triangle tending to know when the cosmologists would have done their calculation, their recalculation?
Sir, the 180?
180, yeah, duh. 180. So that's why they're able to conclude that it is flattening the universe. Let me go again. I don't know how many of you like the mathematics. And this is what I'm going to ask you to do is to rewatch the videos. Let me see if I can find something here just to share with you. Mathematically, it can. Oh, come on. You know, sometimes I get very annoyed with my computer at times. It has a mind of its own. All right, I muted you. All right. Sorry. Asia, I'm going to ask you to do something for me, hon, please. I'm going to ask you to share your screen, but I want to show you. I want to give you something more specific to share for me. I'm seeing it, but I'm seeing one, but let me just. I don't want to get into anything too heavy mathematically. All right. I want you to put in for me. Let me just use the first one here. I want you to put in spherical. Hold on. No. Sorry, I'm looking at it. That's not what I want. So let me just find the other one. All right. All right. Put in spherical, SPHERICAL, spherical geometry in navigation. Spherical geometry in navigation. I just want to show you something. You see if that can. See if I can do something simplified. Gauss theorem. Got me, Asia? Oh, thank you.
In YouTube?
Yeah. Got it. All right. You can look at that video outside of class. I don't want to get into the first one I want to show. You can no, don't click on it yet. Don't click on it. I think it's 7 minutes. Yeah, seven almost 8 minutes long. You can look at it outside of class. What I'm showing you here is if you look at the globe, the image to the right of the first one, you can see at the top, at each corner, you see a right angle triangle. True or false?
True, sir.
Yeah, man. So you see a right angle triangle at each corner of the sphere, of the triangle, on the sphere. All right. So what I'm saying to you is, what is the measure of a right angle in degrees?
90 degrees.
90. Good. Everybody knows that. A right angle measures 90 degrees. How many right angles do we have in the sphere, in the triangle and a spherical diagram?
3.
3. 3 nines? So 27.
27.
Good. So you have 270 degrees in a triangle, in a spherical triangle. You follow what I'm saying? So in a spherical triangle, you're going to have 270 degrees because each of those corners measures 90 degrees. So you can do the mathematics you can look at the video to see the mathematics why each of those angles measures 90 degrees. That's not the point I'm trying to get at. Some other time we can get into that. The point I'm making is, for the sphere, we have 270 degrees to talk about, because it is each vertex, and you have 3 vertices. Where 2 lines meet is a vertex. So each vertex measure 90 degrees. All right? So you have 270 degrees to look at. Now, when you look at a right angle triangle, rubbish is, when you look at a triangle that is drawn on a 2-dimensional figure, what is the sum of angles in that triangle for 2-dimensional?
The 180.
180.
It's 180, yeah. So you recognize that this is a sphere. Look at the first something. Look at the globe. You recognize it's a sphere? And I want circle here is a sphere. Right? So when you, all right. I'm not gonna get this enough because now I'm a maths teacher too, so I'm not gonna get this. All right? Want to work with me? Want to work with me? Want to have a picture me? You have a gum ball, one of those big gum balls. All right? Picture me now. Don't make me lose enough, or you don't lose me. At one end, no lie, there's no end in the sphere. What I'm gonna do, I'm gonna find the diameter. What is the diameter? So the line running through the center of a circle, touching both ends of the circle, don't it? The diameter cuts the circle in half. True or false?
True.
Yeah, man.
True.
So what I want you to do is a picture. Oh, I forget that forgive me. You know, I forget that I have a writing tablet. I forget I have a writing tablet. Forgive me. It's because it's not a math class. Normally when I have a math class, I'll just open, just do the thing. What I'm trying to do is to simplify the first video for you so that you can go back, look at it one more time. Where's my writing pen? Asia, honey, I will ask you to stop sharing for me, please. Thanks. You've been such a good help. I'm going to buy a bag of tickles here. Just, you know. Oh, man. I hate when my system mix up. Give me just half a second. Microsoft Word is not responding. It happens every time I first open the application. Right, just try this again now. Oh, come on. Okay. Just relax yourself and just be a good student. You see, now if I had planned this from before, it would have been, I would have had it up and just move across. What I want you to get from this, you know, is it is science. It is very experimental. Let's try this now. Seriously? No, just relax yourself now. Journal. Are you seeing my screen, guys?
I think it's loading.
Yes, sir. See your screen.
All right. Are you seeing a blank screen? No?
We're
Microsoft
seeing
document?
Zoom. Zoom is over the document. I think I can click the document and see if it will.
I'm actually clicking, but it's not 7 nor 11. It's all right. Let me just see if I can. But it's I'm typing, but it's okay. All right. Are you seeing it now?
We're seeing where you're typing, but it's through Zoom. But I think we can work with it.
But you can see the cursor on it?
Yes, sir.
Yes,
Can
sir.
see a blank
Okay, all right,
space.
okay, all right, good. All right, so that's part of the problem here. This sometimes it just honestly.
See it fully now, sir.
Right. Let me see if I can just use this thing here to hit my shape a little. Let me see if this will work with me. All right, so can you see that?
Yes, sir.
All right, so let us create drama now when this is not going to work. All right, so you see. Say I call that the center of my sphere. Do you agree that this is a sphere? I'm trying to put a three-dimensional idea on a two-dimensional figure, so it's going to look off. So if you did technical drawing in high school, it may help you to see three-dimensionally what I'm trying to achieve. All right. So what happens is that if I have this line drawn from my gumball is what it is that you're seeing here, right? And this line is where I'm going to stick a pin right here. So I'm sticking a pin, right? And I'm finding the center of that. And then now I'm going to go to something here on the other side. This piece here is going to be a right angle. So I'm cutting out a section of my sphere, and I'm going to end up getting my right angle right there, right? But what I'm saying to you is, when I complete this triangle and I cut out something here, I flip the circle around, I'm still going to get a right angle right here. And when I flip the circle around this side, I'm still going to get a right angle. And if the angle measures 90 degrees, it means that I have 3 times that 90 degrees. And 3 times 90 degrees is going to give me 270 degrees. All right? So what it is saying is, based on what is happening, you know that when you draw a triangle, you're supposed to get 270. But each time this triangle is drawn on a flat surface, irrespective of what this A, B, and C works out to be, A plus B plus C is always going to be equal to 180 degrees, because the sum of angles in a triangle cannot be, in two-dimensionally, cannot be less than 180 degrees, cannot be more than 180 degrees. So what they're saying is, because of this stretching, when they look at these 3 points, and in mathematics we say these 3 points are concyclic. When they look at these 3 points, instead of adding up to the 270 degrees, it is coming closer to the 180 degrees. Are you following where I'm going now?
Yes, sir.
So because of that move from the 270 going to the 280 to the 180, it is suggesting that what? What is it suggesting? That what?
It's flat.
It's flat. So that's what mathematically the first video was showing us. That we know it's a sphere. But when we look at these points as a result of the inflation, and we do the calculation, and trust me, you have instruments out there that can do the calculation of those angles. You have software out there that can do the calculation of those angles. And when they do the calculation, it is coming out to be closer to 180. All right. So let me just point out one such software. All right. So I'm having my circle here, and I'm saying to you, if I were to select, say, do that first, do that after, do this next. Display, no, construct, measure. All right, angle B. All right. So what they're saying is that the measure of this angle, the measure of angle B is 70.88. This angle here is 70.88. The measure of that angle is 70.88. Watch me now. When I measure angle A, angle A is giving me 52.42. Do me a favor. I want somebody to add up 52.42 and 70.88 and tell me what to get, please. It's just a point I'm trying to bring across. I know it's not a math class. Please don't rush me. It's just a point.
123.3.
I'm going to subtract that from 180. What to get?
56.7.
All right. So it means that angle C must be 56.7. It means that angle C must be 56.7 or close to. Is that 56.7?
Yes, sir.
Yeah, a negative.
It is 56.7. All right. So what I'm saying to you is that, so even though this is a circle, this is a flat piece. So angles in a triangle have to give me 180 degrees every single time. Now watch what is happening here. Now I want you to watch what is happening. You see what is happening to the angles up here? Watch, look on it. What is happening to those angles up here? You see them moving?
Yes, sir.
Yes, sir.
You see them moving? So do me a favor now. When I add up 109.12 to 37.79 to 33.09, I get exactly 180 degrees. If you don't believe me, you can check that. Check those angles there. 2 9s are 18 and 220. Carry the 2, 2 and 1, 3, 3 and 7, 10. Carry 1, this is 110. This is 117, 137, 147, 150, 150 plus 30, 180. So this adds up to give me 180 degrees. It doesn't matter if I move my C and carry it there and do that, all of these will add up to 180. What's the point I'm making? The point I'm making is that any triangle drawn, random or otherwise, the sum of angles on a two-dimensional figure is going to give you 180 degrees, no matter where. So cosmologists have software, just like our teacher have this software, just like we have this mathematical software. Cosmologists have software that they can click on 3 different points and they can do the same animation. Let me see if I can animate. Lord, help me. A long time I use this enough. Transform. I should be able to animate. Anyhow, if they can animate this in space, animate points. See what is happening there now? So what that is doing is giving you multiple different angles or different shapes of that triangle. By the way, are you seeing my screen?
Oh, yeah, man, sir.
Yeah, man. So I can give you multiple stuff, but every time you add up all of these things here, it will always give you 180 degrees. So if I stop it right here, so that's my triangle, and I choose to stop my triangle right there. And I decide now that I'm going to check the angles. Somebody do it for me, please, because I'm not doing it. I want to prove the point. Somebody add up 16.50, 16.60, and 146.91 and tell me what to get.
Sir, 180.01.
180.0, which is 180 degrees.
Yes, sir.
Which is 180 degrees. So I'm saying to you that cosmologists have devices such as these, because one may sit down and say, then also I talk up in place like they're going to sit down and use protractor and compass and measure something. No, the technology is out there. Just like who I can animate, and guess what? When the man them do it and stop the animation like this and start play it again and say, stop. And then out of them something here, they're going to get the same thing and them say, here the plan. They could move this point and put this point out here as a starting point. I will add up this, then get the 180, and then start to animate, and then say, no, look for one. But if I do that, I still going to get the 180, and it moves around, and they can stop it random. 126 plus 18.14 plus that will give you again 180.01 degrees, right? So this is what they do, and they come up now with the fact that here the plan. Oh Lord, can I do it can I do the sphere in here? Oh Jesus. No, I can't do the sphere. If I can do the sphere in my geometry sketchpad, I would have done it and show you. So the sphere, we know mathematically that each angle in a sphere measures 90 degrees, which gives you a total of 270 degrees. But they recognize that at 270 degrees, when they are doing their animation and doing the stuff, they recognize we not get 270, we're getting closer to 180. They may not get exactly 180 degrees, but it is definitely not 270. It is closer to the 180. So they can come to the conclusion that because of inflation, there is a flattening of the universe because it is done mathematically. Can I assume that based on what I show you just now with the animation of my circle here to show you that it's an experiment that I can do and just randomly stop it at any point in time and add it up and get my 180 degrees, that the cosmologists them have similar devices such as these that they can go and experimentally do them calculations and tell us, here the plan. The universe is flattening because of inflation. True or false? Is anybody convinced? Is anybody convinced yet?
Yes, sir.
Yes. All right. I hear the same voices answering me. What about the others? Davio, what say you? Oh, remember, when I call upon you, don't answer me, I put in a waiting room here. What say you? Alexia, what say you?
Sir, I answered earlier, I agree.
You did. Janelle, what say you?
I agree, sir.
Yeah, I agree? Okay. Davia, what say you?
I agree, sir.
Okay, thank you, please, miss. I just said, no, while ago, because I say, like you want to get a sit out. Carol, what do you say?
Sure, I agree.
Yeah, man. So, so sometimes when you watch the things and we look at it, we're saying, but how the man them going to know? Best believe they have devices out there that they can use. They take, just like radiologists, they can take measurements from different masses in patients, and they can say, no, this mass has grown by 2 centimeters, because built into their system are measurements. Just like how I can click on measure and get my measurement. They can do the same thing in order to measure any 3 points, and they can come to their conclusion. So yes, it is. There is a flattening that is taking place now. What can you tell me about the empty spaces? The empty spaces that are being created by the stretching of the universe. What can you tell me is happening within those empty spaces?
So can you repeat the question, please?
What can you tell me about those empty spaces caused by the stretching of the universe from the Big Bang? No, I didn't ever think outside of the box. I just think about the thing we just watched a while ago, man.
Yes, sir, we're thinking.
Okay, all right.
Sir, does it have to do with radiation?
No, man, remember, it is as a result of the CMB, the cosmic microwave background. Yeah, man. So we know that it's part of the radiation, and this is what it is. Remember the picture that I sent, the picture that I sent to you last class? Yeah, man. Good. So those are it is a CMB that they're using in order to speak about the inflation, You remember that reference is made to the CMB, the cosmic microwave background, that they're using now to talk about the inflation. So when they're looking at different points on the CMB, based on the background that has been created as an aftermath of the Big Bang theory, is what it is that they're going to be talking about with the inflation. So what I'm asking you is that these empty spaces created by the stretch of the universe is where you will visibly see the inflation taking place. Do you agree with me? No?
You can repeat it. I didn't quite understand what you said the last way.
What I'm saying to you, the cosmic microwave background is as a result of the Big Bang theory. And I'm saying that from the Big Bang theory, we are hypothesizing that, and Hutton is, they are saying that the truth of the matter is, yes, the universe is stretching because it started off at one spot, something catastrophic happened, then you have a blasting of this spot that creates multi spots, and these spots that are created now are going to be the formation of galaxies and stars and you name it, right? So I'm saying to you, last class we spoke about the blasting. When we look at them, they are recognizing that there is a gap now between these galaxies that are created from the Big Bang, and they're recognizing that the space between these galaxies and stars and you name it are expanding. They are not constant, suggesting that the universe is stretching. There's a stretch in the universe. All right? That's from the Big Bang, in essence. In essence. What I'm saying to you is, it is the stretching as a result of the Big Bang. We have the CMB that is as an aftermath. This aftermath from the cosmic microwave background is what it is that they are looking at in order to spot the whole business of inflation. Mathematically, they can look at it to say, here the plan. On a sphere, we know that is 270 degrees. 3D, it's 270 degrees. Sum of angles in a triangle, the spherical triangle adds up to 270 degrees. Sum of angles in a triangle in a 2D dimensional space, which is flat, is 180. So on this microwave, the CMB that they look at, when they are measuring the stuff, they recognize that the value is coming closer to 180, if not 180. Can't get less than 180 now, because 180 is going to tell you that the sum of angles by law adds up to be 180. But when they're looking at this stuff, they're getting angles between 180 degrees and 270 degrees. But the value is coming up closer to 180, suggesting that the universe is not spherical as a result of what the catastrophic event that has happened. It is more flattened because it's not close to 270, but closer to 180. You know, we can't get it any simpler. Anybody see that? Everybody understand that?
Yes, sir, I get it.
If you don't understand it, say something to me, please, because I need to move into something else.
Understand.
Right? So so in the video, he spoke about negatively curved, positively curved. He was speaking on the same thing that I was just talking about. Based on the calculations that are done, you can actually get angles that are somewhat warped, because you know that you're supposed to have angles that are supposed to be 90 degrees. The spherical angles in a triangle are supposed to be 90 degrees. You can say whether or not those angles are convex or concave. And he did show an example of being convex or concave, right? Negative rotation and positive rotation. Those are heavy mathematical stuff, but not heavy that you can't understand, right? But simplistically, what I can say to you is that the spherical triangle adds up to 270. Triangle on a flat surface, which is 2-dimensional. The spherical is 3-dimensional. And the sum of angles is going to be 180. The different calculations that they do, animating the stuff, similar to what it is that I would have done here. And if I can find a video, and maybe you guys are very good at it, if you can find a video, what they could, showing you how it is that they do the calculations, in the inflationary, period here, what it is that they're calculating. And it is still going on now. They're actually doing these calculations every day. So it is that they're actually developing their theory, all right? That it is more flattened because of the value that is getting to closer to 180, all right? There's something that I need to bring up. Let me do a new share.
So wait there, sir. Even though this might not be so related to what we're saying, we just kind of pop up in my mind. So that means they agree with our Christopher Columbus, so they agree with them.
Talk truth, right? You see, it is one of the things that I know is, had the universe been very flat, it means that at some point in time, you can drop off, and there's no dropping off. So we know that there is some level of spherical shape to it, but it is not fully spherical. So yes, his hypothesis to say that the place is flat, we're going to throw it out, because when you look beyond the horizon, think of it this way. Think of it this way. If you look at the horizon there, and you say, okay, fine, I am going to test this theory. I am going to go on a speedboat with enough gas oil and enough and a metal suit with whole heap of oxygen. So in the event that we capsize, we don't play any games with any sharks and all them ugly creatures that are down there. So we have a cell phone, and we have internet, and we have WhatsApp, so we can WhatsApp and say, here the plan. Man is down, and I'm this place, and I can send my location like you can do on WhatsApp, so the rescue team can come and save me. So we can sit down and look on the shark and say hello. If something like that can be created, sure, I will go all the way out there. All right. So let us put an ideal situation. So we have all of that. We have all the gadgets that should, in case we get lost, we can just say, here the plan. So my live location here, come find me. All right. When you go to that horizon, you recognize that you cannot reach that horizon, because the closer you think you get to the horizon, to the point where you are lost in the horizon by somebody that's on shore, you are still seeing another horizon, so to speak. So it gives some sort of definition that the sphericalness, so to speak, of our planet. But scientifically, the man them coming up with some other findings. Don't know if that make any sense, but that's just what it is. And we have to go by the data. And Paul, the truth of the matter is, when we look at the creationary theory now, it's going to put a whole lot of things into question, as to what is what. Is this thing real? And every time I think about it, I get a little upset. But the creationist view, some scientists are believing that there is no God. A lot of scientists believe that there is no God, and I'm saying a little knowledge is good enough. But when you have too much knowledge, it starts making you move away. And the truth of the matter is, most of these scientists are atheists because they're saying, I can prove to you that there is no God, because
yes, sir. Some of them, because them with them science. So them believe in them sciences. So some of them really and truly don't believe that there is a God. Them believe in like proof, and when you can prove it and then something there.
And what you're saying, Karen, is that they can prove that there was life form before God. They are going to say that they can prove life form before God. But you see, the truth of the matter is, when I was doing some reading, sorry, you have some creationists who creationists view that, saying that yes, God spoke these things into being, and they came to the fore, so to speak. So God spoke some things into being, and it came into existence. So this document that I sent to you, I want you to read it. Why I still doubt inflation in spite of gravitational wave findings. And this document is from 2014. You can find other documents that are closer in age to show you that there is work that is being done on the whole business of inflation. I'm trying to show you something that you have this document in the stuff. I give it a link to it.
Yes, sir. I tried using the link and it wasn't working.
No, man, you have to press Control. You have to press Control and then click on it. That's what I did a while ago to bring it up. I'm trying to find, oh Lord. There's something in here. All right, so again, just reading this document tells you that the Big Bang occurred before the inflation. Inflation has always been more productive imagination than empirical evidence. All right, so it's always good to get a viewpoint. Let me just read something very quickly here. It says, proposed more than 30 years ago, inflation holds that an instant 10 to the negative 43 seconds, according to one estimate. After the Big Bang, gravity flipped inside out, briefly becoming a repulsive rather than attractive force. As a result, the cosmos underwent an almost unimaginably rapid growth spurt, which has profound impact on its evolution before slowing down to a more leisurely rate of expansion. So we know that it is saying that there is expansion of the universe, but as a result of that, there is some levels of slowing down taking place. Many cosmologists fell in love with inflation because it seems to solve riddles posed by the basic Big Bang theory. Why, for example, does the universe appear so uniform in all directions? You remember the video spoke about uniformity?
Yes, sir.
All right. Now, my mathematical explanation about that uniformity is that you remember the animation that I gave to you just now, that I showed to you just now? When they are looking at those animations at different points in the CMB, the cosmic microwave background, they are coming out with values closer to the 180 degrees. So which is why they are saying that it seems to solve the wrinkles posed by the basic Big Bang theory, because they believe in the inflation. Why? Why does the universe appear to be uniform in all directions? The answer is that inflation would have smoothed out lumps in space-time, just as blowing up a balloon smooths out its wrinkles, right? So this smoothing out of the stuff is also causing the flattening. So when you have a lump and you smooth it out, don't it becomes flat? Talk truth.
Yes, sir.
Yes, sir.
Yeah, man. Good. So it says, but inflation has always been a more product of imagination than empirical evidence. There has never been more than circumstantial hand-wavy support for its core mechanism, the reversal of gravity. Worse, the theory came in many different forms. It says, my favorite was the eternally self-reproducing, chaotic, inflammatory multiverse that don't help me know. Yeah. So Mr. Andre Lindy, oh come on, is one of those pioneers. Oh Lord, as it relates to the inflation, as well as Mr. Allen that we just looked at a while ago, right? So the pair created inventing inflation, and you can look at that. You can, when you click on this, this computer is going to allow me to speak in tongues. When you click on this hyperlink, you will see more on what it is that these three are talking about, right? And which is I'm saying to you, it's very important that to read. We can't just come and just take one view and just move with it. We have to take many views in order to concretize our understanding. It says just 2 months ago, inflation pioneer Paul Steinhardt wrote on the website, what is happening? All right, it says, talking about some theories to determine the inflation and string theory can be saved from developing into a theory of anything. All right. And as I said before, see, Steinhardt did something in 2011. How far is 2011 from us? Just 11 years ago. Just 11 years ago. And I can tell you, you can find articles even closer than this one here. Right? There was something, however, all right, so this one is saying that why they are disbelieving you notice the title of it? Why I still doubt inflation in spite of gravitational wave findings. This one here is saying that, I saw something, the CMB. He was saying that the leftover form just after the Big Bang is known as the CMB, the cosmic microwave background. This pattern basically occurring in the polarization or orientation of light can be created only by gravitational wave produced by inflation, right? If corroborated, David Overby writes in the New York Times, Bicep 2, and you can look at that. And he was saying that the discovery of the dark energy pulsing pushing the environment, the universe apart, or of its Big Bang itself, it would open vast realms of time and space and energy to science and speculation, right? So we have to look at different views. One is saying that here the plan, it exists, and the other one say that, you know, I kind of still have some doubts because of these gravitational waves that are still present. So the guys are looking at what is happening. And this one is talking about the mathematical universe. I will soon look at that. I want to spend some time on the creation theory, but all right. you can go through. I can't find what it is. I should have highlighted it. I can't find what it is that I wanted to talk about. Let me just click on this mathematical stuff. And see if it brings up. Sorry. All right, so while that comes up, all right, are you seeing the screen? I need to do a new share.
Yes, sir.
Yes, sir.
All right, cool. It's the first time looking at this one here, so let me just see if I can spot out something. Or mathematical universe. Boy. Speculator is successful at describing the cosmos. You see all of these people. Anyhow, let me hold that until I reach creationist theory part. All right, so you have all of these people who clearly have some interest in the mathematical definition of what is happening here with the universe. All right. Allow me though to, I mean, this is pretty good. I think we would have gone through some stuff with the Big Bang theory. We look at the inflation theory, what people are saying, but also need to look at the pros and cons. One possible question that they could give you is argue for or against inflation resulting from the Big Bang theory, right? So you need to, so if you're arguing for, you need to bring your arguments for it, and you also need to, you would have to make mention of something that somebody is saying against it. So for example, you can, if you're arguing for inflation, you can make reference to this article here that according to who this one be now, to John Horgan, who still has doubt in inflation in spite of gravitational wave findings. So gravitational wave findings may be one of your strong points to suggest the inflation theory. You will now have to rebut why you disagree with Sir John, right? So when you're arguing for or against, you will have to look at what your opponents may be saying. Okay, so Sir Hogarth is saying that he does believe in the gravitational wave findings supporting inflation, but he still has doubts. What are his doubts? What arguments can you put forward to counteract what it is that he's saying, right? So it's one of the things that I think I need to help the group, because I'm actually seeing something beforehand. I'm not speaking anything into being, but what I'm sensing thus far is incidentally, the recordings have been uploaded, and what is very obvious to me was last week Wednesday's oh goodness, last week Wednesday this time I think my shoes it was just falling off, but anyhow, was how short the class was, suggesting to me that people just maybe use the opportunity to say, in a day or so we not stay a class, and you know that the 2 hours were not spent. I've seen it. I've seen it. I don't ready to complain to comment fully on it yet, but anyhow. So what I'm seeing happening is the analytical aspect of the students of this class being missing. When you're arguing a point, you may say that your opponents may say smoking marijuana caused me to be relaxed and caused me to be very calm so that I don't act out in a harsh way. But of course, you saw the recent situation where it is alleged that the young man is on marijuana, but snapped and killed 5 people. What when you don't have any marijuana to smoke to calm your nerve? Is it that you are going to be a risk not only to yourself but to others? So you're looking at what your opponents may say, and then you're going to use your opponent's argument to combat something. So you're saying to me that in a split of a second, when there is no marijuana, that you can act irrationally, causing bodily harm to self and others, right? So when you're writing your stuff, you have to be very objective, and you have to analyze the question based on what it is that they are asking. Me making sense? Anybody?
Yes, sir.
Oh, okay. All right. Just yeah. And what is so concerning also, let me see if I can go back to that document and just wrap up this. I don't want to come back to it. What is so concerning is that it's the same people saying to me, yes, sir. I want more of you to be responding to me. I want more of you to be responding to me. All right. Okay. Are you seeing my screen? Creationism?
Yeah, creationism.
Right. Somebody just reminded me of something that I did not speak on the steady state theory. You're not seeing the screen, so let me just show you this. As I said to you guys, let me just confess something to you. There's no way I can overteach this course, because you see, when you look at one thing, it brings up a question about something else. Last week, Monday, when I was asking the question, I remember when Mikey was explaining the whole Big Bang, and one of the terms that he used is something catastrophic happened, right? So right there and then, he's talking about the Big Bang theory, and he's now bringing in catastrophism into that explanation. What's the point, sir? The point is, you're explaining one theory or one concept, you have to rely on several other concepts in order to bring across your point. So you can't just talk about Big Bang in isolation. You can't talk about Big Bang without something catastrophic happened. Why it is that this spot split into many different pieces, right? And the heat that was generated in splitting this, bond breaking and bond making, you can't separate that. And you can also separate the after effect, the CMB, the cosmic microwave background. And outside of that, you can't not talk about inflation, right? And outside of that, you can't talk about the whole business of creationism. So one leads into the other. So you have to get the full picture, right? You have to get the full picture of what it is that we're talking about. All right, so someone just reminded me about the steady state theorem. And I'm just going to talk about it just briefly, because I really want to look at even very briefly talk about the creationism. It says a steady state theorem in cosmology is a view that the universe is always expanding, but maintaining a constant average density, with matter being continuously created to form new stars and galaxies at the same rate that old ones become unobservable as a consequence of their increasing distance and velocity of recession. Some may also say that they die. All right. So it is that you can have new ones, space for new ones, because if they weren't dying out, it means that you'll have a gazillion of them there. So some would believe that they are dying out, and I believe that they are dying out. Why I say I believe that they are dying out? Sometimes, and I thank God that I think just Paz, who is one of those who is like me. Sometimes I go outside and I look up and I say, okay, fine, that is my friend. I'm going to call my friend Horton. That is my friend Horton. And I'm going to be looking at Horton and say, hey, Horton, find a girlfriend. That is Andrea. And then no, I'm looking at these two stars. I'm really just there to go out and I'm just lounging and I'm, just looking at God's creation. And then after a while, I can still identify Horton. But at some point in time, I can't say Andrea. Cockroach, Iman, Horton not talk again. There's trouble in the camp. Horton find a new girlfriend, or is it that Andrea move out, right? Because after a while, you may have these things just moving far from each other because of the whole stretching. And as it says here, old ones become unobservable as a consequence of their increasing distance and velocity of recession. So the steady state theorem is saying that the universe is always expanding and maintaining that constant average density. Rockstone, constant average density. So it means that the weight of the universe is constant, right? With matter being continuously created to form new stars and galaxies. Now, if it is maintaining this steady and this constant density, which is really the weight, but matter being continuously created to form new stars, it means that some of them are going to dead out. Talk the truth.
Yes, sir.
Yeah, man. Because if it is always expanding, maintaining a constant average density, but matter is being, and matter is anything that has weight and takes up space, right? So matter is being continuously created to form new stars and new galaxies. New stars, new galaxies are being created, but the density is still the same. That means some of the ones that were created before must have died out, making space for new ones, at the same rate that old ones become unobservable as a consequence of their increasing distance and velocity of recession. So chances are that they are dying out. Is this question, I don't remember who asked me in the group, sent me a private message, sorry, you didn't speak about the steady state theory. By the way, am I making sense with the steady state theory right here?
Yes, sir.
Right. And incidentally, sometimes on the exam paper, I know they used to do this a lot at university. They will give you on the exam, they will give you 5 things or 6 things, and they ask you to write on all 6 of them, or you know, these are short answer questions. So they'll ask you to explain, giving suitable examples of steady state theory. So you have to explain to them what the steady state theory is and explain to them, so you're gonna talk about the analysis of it. So you can't just go on Google for arguments. I never just want to know. If anybody who write my paper and go on Google and take off the answer on Google and you just fail. Sorry, let me say that in English. Any of my students who think that you're going to pass my course by just going on Google to get the information and just give it to me and present the information to me like it's theirs, you just failed. You fail before you even do the exam. Because my question, you must internalize and tell me what is happening, which is why I'm explaining this stuff. You have to give me some examples, and you have to demonstrate to me that you understand the material. Guys, I had to understand the material in order for me to finish off when I was studying. And I keep telling my students, when I was going to university, when I was completing my first degree at the university, we did not have computers. The first computer I worked with in the department was in my final year when I was doing some GIS. Final year. Final year. All right? So most of this information I had to go to the library, read it, make notes, understand it, and be able to internalize it. So if it is being asked of me, I can regenerate it. I want you to be watching these videos, understand what it is talking about, and come on the exam paper and explain to me, and know so you understand. And I'm saying this again, if any one of you think that you can go and copy anything from Google and give it to Sir Shant and think they pass the course, remember, say you fail already. All right? Just saying. So I asked the question, what is the difference between Big Bang and the steady state theory, right? In the steady state, we're continuous creation of matter. Oh, sorry, before I go there, I was trying to give you another example before I remember this exam based on Google. So when I was growing up and I heard about, by the way, let me ask you, what is the population of Jamaica?
They're 2.1 million.
That's what I grew up to hear. I hear 2 million, I hear 2.1, I hear 2.5, I hear 2.6, and sometimes I even hear 3 million, right? No, let us use 2.5 million as an average of the different estimates that we're getting. And they're doing a census now, so they can give us an idea as to what it is like. And incidentally, that's why I love the United States for some things. Say, for example, Asia, you live in Cherry Gardens. All right? You can go, if you're in the States, no, sorry, they don't have Cherry Gardens. No. All right. Say you live in Fort Lauderdale. Say you live in Margate in Fort Lauderdale. What you could do, is to go on the USGS, United States Geological Society site, and you can actually look at the population in Fort Lauderdale. But guess what? You can get nitty-gritty and say, here the plan. I live in the city of Margate. You can go and you can click on Margate, and they can tell you the population in Margate. How can they tell you the population in Margate? Because they know the number of houses in Margate. They know the number of houses in Margate. And guess what? When you go to Margate, Margate is a senior citizen city. So you have a lot of condos, a lot of condominiums, all right? And in the condos, they stipulate no more than 2. And you can have your family visiting, but you have to declare the number of residents in there. So they have that information. So their site is very updated. Now, when a child is born, the information is uploaded to their site. So they can tell you the population in any city, in any state, at any given time. Now, fast forward to Jamaica now. From I was growing up, I'm hearing that we have 2 million people. And I'm saying, but from the time you grew up till now, yesterday born, how we still have 2.5? The truth of the matter is people are dying, talk truth.
Yes, sir.
And people are migrating down.
Yeah.
And people are immigrating down.
Yes, sir.
And with what is happening with some of our young people now, they are multiplying even at a faster rate than they're supposed to be multiplying. If you go to China, for argument's sake, they will say to you that they limit each couple to 1 child.
A certain amount of children you have to have.
Yes, ma'am. So sometimes, as matter of fact, I've heard a situation where, I don't know if it is true, you can confirm it and let me know in the other class, that because of the COVID and so many people died, that they are now encouraging families now, the band are encouraging families now to have more children because of the population, the decline in the population as a result of the many deaths that they have. So they are very serious in terms of population control. So you can be charged if them say you can only have 2 picnics and you decide say you want 3, right? And then no, it may mean that it becomes so costly for you because they are going to be taking care of 2. And the 3rd one, you depend on your own, right? So, it's a matter to be discussed, right? As I said before, we just don't have enough time to go through this. But let me just do another 2 or 3 minutes on this. I know you have another class. So it says that in the steady state theory, with continuous creation of matter, and it's what to talk about the continuous creation of matter, more people are having more children. Because of the stretching, you still have more galaxies and new ones that are being formed, new stars that are being formed, all right? There will be a mixture of young and old galaxies throughout the universe. Don't that make sense? You have mixture of old people and new people, young people, talk truth.
Yes, sir.
Yep.
So in the Big Bang, with only an initial creation, galaxies would age with time, right? So what it is that is saying here, so they're asking what's wrong with the steady state. So in the steady state, the universe always the same, so it never produced a black body. Hence, the existence of a black body background rule out the steady state. In addition, the temperature of the cosmic background, microwave we're talking about, can be measured in some very distant clouds that produce absorption light in the spectra of quasars. No, so it is. You have to understand that matter is being birthed continuously. So in order for it to maintain that steady density, it means that you will have had these galaxies and these stars dying out or aging with time, as it says here, making space for new ones that are coming up. Because if you don't create space for new ones, it means that you will have an overload in this galaxy. And guess what? The truth of the matter is, if it is continued to stretch, and it has not yet reached its elasticity point, it means that you have much more space for new matter to be birthed, right? So look at it. Again, my creationist theory is being pushed off. What I'm going to ask you to do for me, I won't spend a whole class on Monday, God's willing, to go through the creationist theory. And remember, we need to do a little makeup class one of these Fridays. This Friday is not going to be good for me because of a training session that I have to deal with matters concerning you and your timetables for September morning. So this Friday is not going to be good for me. I was hoping that I would have link up this Friday, but forgive me. I want you to read up on the creationist theory because, I mean, as I said before, one of the questions that you could possibly get is compare and contrast the inflation theory and the creationist theory. Compare and contrast something else, right? So you have to understand in order for you to compare and contrast, right? And they may ask you to compare and contrast in no more than 150 words. So when I ask if you go on Google, if you go take off from Google, we want you to compare and contrast what is happening. All right? Have a good one. I won't keep you any longer.
All right, sir.
All right, thanks, guys.
Good evening, sir.
Yeah, take care, guys. Thanks for coming out. You call me right on time. All right.